Welcome back. In the video of today, I'm going to talk about constitutive modeling. Different materials behave differently under the same stress conditions. This is a particular feature of each type of material. When we apply the same stress, they behave differently. They deform in a different way. What we want to do here is to define a set of mathematical equations that behave in a similar way that we observe in laboratory experiments, for example. What we want to do is to come up with a function that receives a stress tensor and produces a strain tensor that is comparable to our observations. This is what we call a constitutive model. It relates stresses to strains. The focus of this presentation is on constitutive modeling of salt rocks. So to develop a constitutive model for salt rock, first we need to understand the mechanical behavior of salt rocks. We need to understand what types of deformations that we want to capture or to describe. Are they elastic deformations, inelastic deformations, time dependent, time independent? What types of deformations? So I'm going to present the mechanical behavior of salt rocks from a high-level overview. I'm not going into the details of the micromechanics. I just want to show the basic deformation mechanisms that we can identify in a salt rock. So that establishes our target. So we know what we want to model. After that, I will present some intuition about basic elements that we can use for that modeling. I'm going to talk about springs and dashpots and combination of springs and dashpots, friction elements. I will show some the intuition behind the mechanical behavior of those elements. Then I will show detailed equations so that we can really understand how those elements behave. And then once we understand the behavior of each element separately, we can think of how to combine those elements to produce the mechanical behavior that we want. Okay, so before we proceed, I would like to review some simple concepts that are going to be used throughout this presentation. So the first one is the concept of stress decomposition. We can decompose this stress tensor into a deviatoric part and a hydrostatic part. The hydrostatic part only changes the volume of a certain element. It doesn't change the shape. So the volume, the shape of that element shrinks, or the volume shrinks, or it expands, but the shape stays the same. And we also have the deviatoric part. The deviatoric part, on the other hand, doesn't change the volume of the element. It only changes the shape of the element. So the volume will be the same, but the shape will change. We can compute the hydrostatic part by taking the average of the diagonal values. So this is the average of the diagonal values. We just take the trace of the stress tensor, which is the sum of the diagonal values, and we divide by 3. And this is what we call the mean stress. Here, mean stress. And we multiply, this is a scalar, okay? This is a scalar, and we multiply this by the identity second order tensor. And this is the hydrostatic part. The deviatoric part we cannot compute directly, but we just use the equation to solve for the deviatoric stress. So this is what we do in this equation here. This is the deviatoric stress that we want to calculate. This is the stress tensor that we already know because the stress tensor is known. And this is the hydrostatic part, which also only depends on the original stress. So we take the trace, divide by 3, multiply by the identity tensor. In this way, we can compute the deviatoric stress. Okay, the next concept I want to review is the idea of stress invariance. Stress invariants are some characteristics of the stress tensor or any second order tensor that doesn't change when we rotate our coordinate system. Because suppose for example I have this object here. If I apply a certain stress, a certain loading condition to this object, the stress doesn't change if I change the coordinate system. In fact, in nature, there are no coordinate system, but there are stresses. So there must be something about the stress that doesn't change when we rotate the coordinate system. It's the same thing as a vector. Suppose you have a vector here. A vector has a certain length, and that vector can be represented in different ways depending on the coordinate system. If we rotate the coordinate system, the components of that stress of that vector will change, but the length of the vector or the modulus of the vector doesn't change. It's independent on the coordinate system. It's the same thing with the stress invariants. If we rotate the coordinate system, those stress invariants, they doesn't change. And the stress, so we have for stress, we have three invariants. The first one is the trace of the stress tensor, so just the sum of the diagonal values. The second invariant is the determinant of the stress tensor. And the third invariant is given by this expression here. Okay, this is how you compute the invariant of the stress tensor, or any tensor actually. It's also useful or convenient to us to define the invariance of the deviatoric stress tensor. The deviatoric stress, the stress invariance of the deviatoric stress tensor can also be computed by these same expressions here. We just have to substitute the sigma by S, and yeah, it would be the same thing. It can be shown that if we take the trace of the deviatoric stress, the trace of this tensor will be 0. We can compute the second and third invariant by the same expressions here, but we can also relate them to the invariance of the original stress. And this is what we do here. So the second invariant of the deviatoric stress is 1/3 of the square of the first invariant minus the second invariant of the original stress. It's just a different way of computing, maybe a more convenient way of computing the invariance of the deviatoric stress. And why is this important? Because there are many important quantities that can be represented in terms of those invariants. For example, we have the mean stress, also known as a normal octahedral stress, which is equals to minus pressure, and this is equal to 1/3 of the first deviatoric stress of the original tensor. So this is just the average of the diagonal values, and this gives an idea of how much the stress changes the volume of a certain element. This is the hydrostatic part of the stress. We also have quantities associated to shape change, like the shear octahedral stress, which is 2/3 of J2 squared, or the von Mises stress, which is very common to appear. The von Mises stress is a square root of 3 times J2, which can also be computed by the square root of 3/2 double dot product between the deviatoric stresses. We also have the load angle. The load angle is related to the loading condition. For example, if we have a tensile loading condition, the load angle will be of a certain value. If we have compressive, if we have hydrostatic condition to a certain element below, the angle will have a different value. And it is computed based on J3 and J2, so only in terms of the deviatoric stress. Okay, so keep those quantities in mind. We are going to see those quantities along this presentation. Now let's talk about salt rock mechanics. If we take a certain piece of rock, salt rock, so imagine a cylinder of rock or a cube of salt rock, and we apply a certain stress condition. So suppose the confining pressure, the stresses in the radial direction we apply a certain confining pressure and we apply a certain axial stress. And this gives a stress condition like this, for example. If we know that, if we perform this experiment, we know that every point inside this element here, because of symmetry, because the material is symmetric, we know that every point inside this element will be subjected to this stress condition here. And once we know the stress, we can come into this graph here and compute the first stress invariant of this stress tensor. We can compute J2. We can think of these quantities as the mean stress and the von Mises stress, for example, because they are proportional, right? And once we compute these two values, this will give a point on this graph. And this point can be here, it can be here, it can be here, or it can be here, for example. And the salt rock will behave differently depending on where we are. If we are in the compressibility region, the material will behave more or less like this. So this is a graph that shows time and total deformation. So suppose we are measuring the deformation along the axial direction. If we do that, we are going to observe something like this. The material behaves very fast in the beginning, and then it deforms at a constant rate. Suppose that the stress that we are applying, we are imposing to this salt rock is constant. We don't change the stress. The stress is constant. Even in that situation, the material will constant deform like this. This is called creep. More specifically, this first part here is called transient creep, and this second part where it deforms at a constant rate, it's called steady state creep. If we increase the stresses such that the point lies in the dilatancy region, we are going to observe something like this. We have transient creep in the beginning, then we have steady state creep, and then sooner or later the material will behave like this. The deformation will spike and the material will finally break in a brittle way. This is called tertiary creep. So suppose you are in a salt cavern and there is a specific point on your salt cavern that is operating in the dilatancy region. So the stresses applied to that specific point are in the dilatancy region. That means that that specific point sooner or later will fail. So this compromises the mechanical stability of our cavern, for example. And finally, if the stress point lies in this short-term failure boundary, the material breaks right away. So if you are in this point here, for example, then you increase the stress such that the stress hits the short-term failure boundary. The material doesn't even go through all creep stages, so transient, steady state, and tertiary creep. It doesn't even go through all those stages. It just breaks right away. So this is what the short-term failure boundary is. These two regions, compressibility region and the dilatancy region, they are divided by what is usually called compressibility dilatancy boundary or compressibility boundary. And although we call it a boundary, this is more like a region than a boundary itself, because yeah, the delimitation between these two regions, the latency and compressibility regions, is it's hard to define. Actually, when we perform experiments, some materials make the transition here, other materials make the transition here. So we have more like a region in which we're not really sure if the material behaves in a dilatancy, in a dilatant or compressible way. Uh, Another characteristic of these two regions is that in the compressibility region, the volume of the sample, so notice that in this sample here, we're applying compressive loads in all directions. So if we are applying compressive loads in all directions, it's reasonable to think that the volume of the sample will decrease, right? Because we are compressing in all directions. And this is what happens in the compressibility region. It's not like it will decrease forever. It can also stabilize. It can decrease for a certain time, and then it stabilizes, but it doesn't increase. But if we are in the dilatancy region, then surprisingly, the volume of that sample starts to increase again. And the reason it increases is because in the dilatancy region, the salt rock starts to accumulate damage. You start to create cracks inside the rock, and those cracks, they produce space, so the volume increase, and those cracks are precisely what cause tertiary creep. So when we have unstable growth of those cracks, we have tertiary creep, and this happens in the dilatancy region. Another thing that happens in the dilatancy region is the huge increment of permeabilities. So this is another reason we don't want any point of the around the cavern to operate in the dilatancy region, because it increases the permeability of salt, therefore compromising the sealing capacity of the salt. Okay, so we have these two regions. Uh, yeah, now let's move on to more what we want to describe. So if we apply a certain stress condition, a constant stress condition, this is just an illustration. This is time and this is stress. I'm just saying that the stress is constant. I'm not specifying which component of the stress, but suppose the confining stress or the radial stress is constant and the axial stress is also constant. This is what I'm illustrating here. If we apply a constant stress condition, the material will behave like this. So as soon as we apply the stress, the material behaves instantaneously responds here, and then we have this deformation here. It deforms fast in the beginning. The strain rate is high in the beginning, and then it decreases over time. By strain rate, I mean the slope of this curve is high, and then it decreases over time, and at a certain point it stabilizes at a constant value. While the strain rate is decreasing, we call it primary creep stage or transient creep stage, because the strain rate is changing over time. When the strain rate stabilizes, we call it secondary creep stage or steady state creep. And if we're operating in the dilatancy region, the strain rate can start to increase again, and this defines the tertiary creep stage or accelerated creep. So we have primary, secondary, and tertiary creep. But we have also another interesting phenomenon that occurs with salt, not just with salt, but other materials as well, which is called, which can be observed when we reduce the stress. So if we apply a constant stress, the material will present the transient creep and then steady state creep. If we reduce the stress, the material will respond like this. You see this curvature here, and then it stabilizes again at a constant rate, even though the stress is constant. So to help us analyze this graph, let's mark some interesting points here. So we can see here that from point A to B, the stress is decreasing and the deformation is also decreasing because we are removing stress. So if we are applying a stress, if we are compressing the rock, and then we alleviate a little bit the stress, the material will recover a little bit, which is what we observe here. From point A to B, it will recover a little bit. But from B to C, the stress is constant, but the material continues to recover. So the strain continues to decrease until point C. And from point C to point D, the stress is still constant, but the material continues to increase. So this additional recovery from point B to C is what we call reverse creep. This is what we call reverse transient creep because it occurs when we unload the sample. When we look at laboratory experiments, this behavior here is very hard to observe. It's not so explicit as I've done in this illustration. But when we look at the stress strain curve, it is much more explicit. And when we look in the stress strain curve, we see something like this. So this is the stress, and this is the axial strain, or the strain. I have the same points here, A, B, C, D, E, corresponding to these points here. So let's go through this. In the beginning, we have a constant stress, and the strain is always increasing. So we have a constant stress, and the strain is moving to the right because it's increasing until it reaches point A. In point A, we drop the stress to point B, and at the same time, the strain decreases. So the strain must move to the left, and the stress moves down, right? Because we decrease the stress and we also decrease the strain. So we move from point A to B. Now, from B to C, the stress is constant. From B to C, the stress is constant. And the strain is decreasing even further. You see, so that is why we move to the left, because in this graph that we see that from B to C, the strain is increasing. But then the stress is kept constant. From C to D, the stress has still the same value. That is why we are still in the same line. And from this point C to D, we see that the deformation is increasing again. And that is why from C to D, we are moving to the right again. And when we reach point C, we increase the stress again, and we move up again. So this is a very characteristic of reverse creep. When we look at the stress, when we have an unloading and reloading path on your experiment, and you look at the stress strain curve, if you see something like this is a signature of reverse creep. It presents all those features here. It goes from A to B, and then it moves to the left, and this point C marks the lowest point of deformation. After this point, the deformation starts to increase again. So after point C, it starts to move to the right again until it reaches point C, where the reloading takes place. This is very characteristic. We can see this in laboratory experiments, but I can show you now in a model, in the results of a model that I have implemented here. Let me do this. So, okay, this is let me show this. Okay, so this is a numerical experiment that I have prepared. So this let's forget about these graphs here in the bottom line. Let's focus on the upper line here, upper row. So this is a triaxial test that I am simulating. The radial stress is I apply like this. This is the red curve. The blue curve represents the axial stress. So the axial stress, so both of them increase, and then they are kept constant. The radial stress is kept constant all the time, and the axial stress I decrease, and then I increase again. So let's see what happens. Okay, I want to show this. Yes. Yeah, okay. So this graph here shows the resulting deformation in the radial direction and in the axial direction. And this graph shows the differential stress, yes, the difference between axial and radial stress. And this is the axial strain. So this blue curve here, I'm plotting this axis. We can see that in this graph here, when we start to unload, this point goes down, as we saw in the explanation before, until it reaches the bottom there. Okay, and it reaches this part here. If we look at here, we can see something like this. You can see that the point is here, but from now on, both the radial stress and axial stress will be constant. But still, the material continues to deform. So you see the stress is constant, but the material still recovers a little bit because the deformation is decreasing, is still decreasing. And if we see this part of the graph, you see that that point is moving to the left because the deformation is still decreasing. And it recovers until it reaches the lowest point, which is this one. And this is where reverse creep finishes. This is the end of reverse creep. From here to here, we only have steady state creep. If we keep moving, we see that this point will start to move to the right again, because it's, let's see, so I can keep going. Let me zoom out here. We can keep going until we start to reload again. Let's see. So yeah, so this is a model result, but when you perform experiments, you observe something very similar to this. So this is very illustrative of what happens in reality. Okay, so this is what we call the reverse creep. Okay, let's return to our presentation here. So, okay, so this is the mechanical behavior of salt rock from a macroscopic view. Now we know what we want to model. For example, we want to model primary creep, secondary creep, tertiary creep, and reverse creep. This is what we want to model now. So let's try to understand how we can do this. In this part of the presentation, I will show the mechanical behavior of some basic elements, and by basic elements I mean springs and dashpots, and also some friction elements, some special dashpots that have specific behaviors that we can use. Once we understand them, we can combine those basic elements to describe the behavior that we want. So first, let's start by the intuition behind each of these models, and the first one is a spring. Yeah, a spring suppose we have a spring here, a linear spring. We only consider quasi-static load, meaning that when we apply the stress, we disregard any vibration or advection phenomenon. So we consider that everything is in equilibrium here. If we apply a stress like this, for example, the stress is 0, then we suddenly apply a stress, the spring responds immediately, instantaneously. And when we alleviate, when we remove the load, the spring returns immediately as well. So a spring is fully recoverable and it's instantaneous. So it's instantaneous, it provides an instantaneous elastic response. Instantaneous because it's time independent, and elastic because it fully recovers when we remove the load. Next, we have a dashpot. Dashpot behaves very differently than a spring. A dashpot, you can think of a dashpot as a cylinder with a piston inside, and inside this, yeah, to the left of this piston, between the piston and the cylinder, we have a fluid, and that fluid has certain viscosity. When we move the piston, the fluid passes through the small spaces between the cylinder and the piston. So the smaller the viscosity, the easier the fluid passes through those small spaces. So that's how you can think about a dashpot. When we apply a certain stress, a constant stress, that dashpot will move at a constant rate, at a constant speed. When we remove the stress, the dashpot doesn't recover because there's nothing that makes the dashpot to recover unless we apply a stress in an opposite direction, but that's not recovery. That's just deforming in another direction. That's different from the spring. When we remove the stress, the spring naturally recovers to its initial position, but that doesn't happen with the dashpot. And if we apply a higher stress, the dashpot will deform faster. It will deform at a higher rate. How much higher, it will depend on the viscosity of the dashpot. And the viscosity of the dashpot can also depend on the stress itself. So it can have a nonlinear dependency on the stress itself. But that's another discussion that we are going to have in the next few slides. So that's the behavior of a dashpot. Now, what if we combine those two elements in a parallel arrangement? And this is what we call the Kelvin-Voigt element. So we have a spring and a dashpot in parallel. When we apply a stress here, because we are considering quasi-static loading condition, the stress that we apply here is divided by both spring and dashpot. So part of this stress will be balanced by the stress in this spring and by the stress in this dashpot. The stress in the spring is given by the deformation of that spring. The deformation of that spring is the same as the deformation of the dashpot. This is important. It's all a single deformation here. When we apply a stress here, in the moment that we apply a stress, the deformation on this spring is 0, which means that the stress that this spring produces is 0, which means that the stress perceived by this dashpot equals the stress we apply here, which is the highest stress. So this dashpot will respond according to the stress it perceives. That is why in the beginning, the deformation rate, the speed of deformation is very high. But as soon as this element starts to deform, to stretch, this spring starts to produce a stress. And the stress of this spring plus the stress on this dashpot equals the stress, the external stress. So when this spring is stretched, the stress perceived by this dashpot is smaller. That is why the strain rate here is smaller. The slope of this curve is smaller. And the more we stretch this spring, the higher the stress produced by this spring, the smaller the stress perceived by this dashpot. At a certain point, this spring will be so stretched that will completely balance the external load such that the stress perceived by this dashpot is zero. So the strain rate will be zero by the end when this spring is fully stretched. That is why when we place spring in parallel with the dashpot, we get this behavior. So in the beginning, the strain rate is very high, and then it decreases over time. And when we remove this load, external load, the spring will force everything to come back to its initial position, but it's not instantaneous because this dashpot introduces a time dependency. It's like the dashpot says to the spring, okay, I will let you come back to the initial position, but within a certain time. It will not happen instantaneously. Unless the viscosity of the dashpot, of the fluid inside the dashpot is zero. So the fluid has no viscosity. In that case, the dashpot can move without any resistance. So it would be equivalent to not have a dashpot at all. Okay, but that's not the case. We have viscosity here. So when this spring tries to come back to its initial configuration, it takes time because of this dashpot. Another element that is not so common, but it will be useful for us, is a special type of dashpot that behaves like this. When we apply a certain stress condition, a constant stress, the dashpot initially doesn't deform, but as time passes by, it starts to deform faster and faster and faster. And when we remove the load, it doesn't come back because it's a dashpot. It doesn't recover. And we can think of this dashpot as we can think of the viscosity of this dashpot as a function of not just the stress, because the stress is constant, but of something else that we call damage. And if we come up with an equation for this damage evolution such that damage increases over time, and when damage increases, it decreases the viscosity of that dashpot, the dashpot will behave like this. If damage increases, if somehow the viscosity of the dashpot decreases over time, for a constant stress, the dashpot will behave like this. It will, as the viscosity decreases, the velocity of the dashpot will increase faster and faster. Finally, we can have what we call a viscoplastic element. Well, a viscoplastic element is it's visco because it's time dependent, and it's plastic because it's not recoverable. It's inelastic. From that definition, we can also call a dashpot as a viscoplastic element because it's time dependent and it doesn't recover. Also, this damage element is also viscoplastic. But for the purpose of this presentation, what I call viscoplastic element, it's this one here. Okay, let me explain this. This element is a parallel arrangement between a dashpot and a friction element. This friction element just adds a threshold. So if the stress that we apply to this element is below this threshold, this friction element sticks and it blocks the movement of the whole element. So it doesn't let the dashpot to move. if the stress exceeds this threshold, then this dashpot starts to move. And we can model this such that the movement of this dashpot will be like this. How can we do this? We can think of the viscosity of this dashpot to be proportional to the distance between the stress and the threshold. So the higher the distance between the threshold and the stress, so in this case the distance would be this value minus this value. So there's a large difference which produces a high deformation, right? A high strain rate here. But then we can make the threshold to move upwards, to move towards the stress condition. And when this threshold moves upwards, it decreases the difference between the stress and the threshold, and therefore increases the viscosity of this dashpot, making the slope of this curve to decrease. At a certain point, when the threshold reaches the stress, the distance is zero, and the viscosity of the dashpot is infinite, meaning that this dashpot doesn't move anymore. And that is how we can think of this element here. Of course, this is just an intuition. I'm going to show the equations. It's not as simple as just a threshold. This threshold is not just a number, it's actually a surface, the yield surface. I'm going to talk about that later, but that's about how the intuition, how it works. We can also think about a dashpot, this simple dashpot, as a viscoplastic element in which this threshold is always zero. Yeah, okay. So the friction here, the friction element has always zero threshold. So any stress that we apply here already triggers the dashpot, the movement of the dashpot. And in this case, there is no hardening. Oh, there's no hardening rule here. The dashpot behaves. So the viscosity of the dashpot does not depend on the threshold. The threshold is fixed and equal to zero. But in this case, the threshold moves. It's allowed to move, and the viscosity of this dashpot is dependent on the difference between the stress and the threshold. Okay. So to finish, keep in mind that when I talk about viscoplastic element, I refer to this element. Although the dashpot is also a viscoplastic element and also damage is a viscoplastic element, I will call them dashpot and damage element, or yeah. Okay, so this is works for one dimension, but of course our problems are three dimensional. We have to translate this to three dimensions. So let's see how we can do this. Starting from the spring element, this is an instantaneous elastic element. This can be transferred to the three dimensions using Hooke's law, which says that the stress tensor, second order stress tensor, equals the double dot product between a fourth order elastic stiffness elastic tensor and the second order elastic strain tensor. So this fourth order stiffness tensor can be simplified because the stress tensor is symmetric. The elastic strain tensor is also symmetric, which means that the fourth order stiffness tensor also has to be symmetric. And because it has to be symmetric, we can reduce from 81 components to only 36 components. And because of that, we can use Voigt notation to represent this operation here by matrix vector products. And this is done by this expression here. This is the void representation of the stress tensor. This is the void representation of the strain tensor, the elastic strain tensor. And this is the void representation of the stiffness fourth order tensor for the specific case of isotropic material. So for isotropic material, we only need two constants, two elastic constants, the Poisson's ratio, the Poisson's ratio, which is mu, and E is the Young's modulus. Okay. Yeah. So if we know the stress tensor, the elastic strain will be given by this expression here. We just have to take the inverse of the stiffness tensor, or which is the same as taking the inverse of this matrix here. Often I will refer to the stiffness tensor as the stiffness matrix or the elastic stiffness matrix because we can represent it by a matrix using void notation. Okay, so and this is not this produces exactly the same effect of a unit one-dimensional spring, but this is three-dimensional. We have stresses and strains in the three dimensions, and not just normal stresses and strains, but also shear stresses and shear strains. Okay, now for the dashpot. The dashpot works like this. When we apply if we take a dashpot and you try to move it at a certain speed, you have to apply a certain stress, and that is dependent on the viscosity of the dashpot. So the stress equals the viscosity of the fluid inside the dashpot multiplied by the velocity of deformation or the strain rate. The sub-index here stands for inelastic deformation, but it's the deformation of this dashpot here. So if we know the stress, we can compute the velocity of deformation by this expression here. And the viscosity of the dashpot can also depend on stress itself, which makes the problem nonlinear. Okay, but there is a problem with this formulation, which is suppose we apply hydrostatic stress to a certain element. So suppose we take a cube and we dive it into the bottom of a swimming pool. So we are applying a constant stress. So if the material behaves like this dashpot, that hydrostatic load, compressive load, will make the material to shrink at a constant speed forever until it finally disappears. But we know that materials don't just disappear. It doesn't make sense for the material to disappear. So this is not correct. What we observe in practice is that this dashpot is only triggered when we apply deviatoric stress. So a stress that only changes the shape. If we apply a shear stress to an element, the element will deform at a constant speed, and it will deform, and so on. But the volume will not change. So there is no risk of disappearing. So to fix this problem, we just replace the stress by the deviatoric stress. So whenever you have a stress, you compute the deviatoric stress, and then you can compute the strain rate of this dashpot. Okay, so this is a basic formulation of a dashpot. Now we can specialize this for different mechanisms in salt rocks. For example, in salt rock, we have some very known deformation mechanisms, and one of them, they have to do with the microstructures of the salt, and one of them is called dislocation creep. For dislocation creep, we can think of the viscosity of this dashpot as given by this expression here. And this is A is a material parameter, Q is the activation energy, R is the universal gas constant. T is temperature of the material, and Q is the von Mises stress. 1 minus N. N is a material parameter also. So material parameters will have A and N that we have to choose to match the results, the results of the model with the laboratory experiments. It also depends on temperatures. So we can see that for higher temperatures, we have lower viscosities, which means that for higher temperatures, the dashpot deforms faster for the same stress. And if we have lower temperatures, the material, it's harder to deform the material. You can think of honey, for example, or oil. If you increase the temperature, the viscosity decreases, so it's easier to move oil at higher temperatures than it is to deform oil in lower temperatures. You can think of the oil on your pan when you are cooking. When the pan starts to heat up, the viscosity of the oil decreases. So this is for dislocation creep. You can see that it has a nonlinear dependency on the stress because of the von Mises stress here. And this viscosity is multiplied by the deviatoric stress. So yeah, we have a nonlinear dependency on the stress. We also have another well-known deformation mechanisms in salt, which is called pressure solution creep. In pressure solution, we have exactly the same equation, but the viscosity of the dashpot is given by this expression here. So it has it depends directly depends on temperature, and D is the diameter of the salt grains. So pressure solution is a phenomenon that occurs around the salt grains. So if you have bigger salt grains, the viscosity of this dashpot will be higher, which means that for bigger salt grains, the pressure solution creep will be smaller. There will be less pressure solution because you have less surface available for pressure solution to occur. When you have very small grains, you have more surface available for pressure solution to occur, and therefore you have smaller, and that is why you have smaller viscosity in this dashpot, which means that for the same stress, it deforms faster. Okay, this exponential of Q over RT, this is the Arrhenius law. If you want to look it up, this is called Arrhenius law. Okay, but that gives us the strain rate. What we want to do, what we are mostly interested is on the strain at a specific time step or a time level of the simulation of your solution. So at a specific time, t plus delta t, the deformation is given by the deformation at the previous time plus the time step size, the time step interval, the time interval, multiplied by the strain rate. And then it comes the question, the strain rate evaluated in which time level? In the previous time level t, or at the current time level t plus delta t? We can make different choices here depending on the value of theta that we use. If we choose theta equals 1, this term vanishes and we are left with the strain rate evaluated at the previous time level. And this is called the explicit formulation or explicit formulation in time. This is a time integration method. Explicit formulation. If theta equals 1, if theta equals 0, this term vanishes and we are left with this one, the strain rate evaluated at the current time level. And this is called the full implicit formulation. And if we choose theta equals 0.5, we have an average of the two, and this is called the Crank-Nicholson formulation. Crank-Nicholson is known to produce second order approximation in time, whereas the fully implicit and explicit formulations provide first order approximation. Okay. Okay, let's move on. Now we have the Kelvin-Voigt element. We need to know how to compute the deformation at this element when we apply a certain stress. As I've mentioned before, we assume quasi-static loading condition, which means that the external load is in equilibrium to the stresses on the spring and the dashpot. So the stress on this spring will be given by the stiffness matrix or stiffness tensor of this spring, double dot product with the deformation of this element, which is, I'm calling it viscoplastic deformation because, yeah, but it's the same deformation as the spring and the dashpot. So viscoplastic deformation plus the stress on this dashpot, and the stress on this dashpot is given by the viscosity of this dashpot multiplied by the strain rate of this dashpot or this element, which is the same. They will move together, right? And this is equal to the total stress. So this is just a balance of forces. So we can solve this equation for the viscoelastic strain rate, and the viscoelastic strain rate will be given by this expression here. And we can see in the beginning, the deformation of this element is 0. So this value here will be 0, and the strain rate of this whole element will be given by 1 over eta times sigma. But at a certain point, this deformation will be large enough such that the double dot product between C and this deformation will equalize the stress such that this value here will be 0, meaning that the strain rate will be 0. And this is what happens when we are at the end of this cycle here. The strain rate is practically 0. Okay. Now this is just an ordinary differential equation with a time derivative here. It has analytical solution for this, for a general stress condition like this. For example, if you apply a stress condition in a discrete manner, which is usually the case, the analytical solution is given by this expression here. So C bar is given by this expression. So we have 1 over 1 minus exponential of minus Young's modulus of this spring, the viscosity of this dashpot, time multiplied by time, and everything multiplied by the stiffness matrix of this spring. This is what C bar is. So we can just take the inverse of this matrix here, multiplied by the initial stress that we apply, and then we can have a general stress condition like this. And this I am illustrating just one of the components, but this is actually a second order tensor. So we can have any type of tensor here, any type of stress condition. So for each time Ti, for example, suppose this is Ti, we evaluate this function at Ti, and we have a summation from j equals 0 to I minus 1, so j equals 0 to until this time. So it has a time history dependence here. And this function here, C bar will receive Ti minus Tj, and double dot product with this stress increment here. So this gives an analytical solution for the mechanical behavior of this Kelvin-Voigt element here. Okay, let's move to the next. This is the dashpot that describes damage evolution. And just like any other dashpot, we can think of the strain rate as 1 over viscosity multiplied by stress. And 1 over viscosity is given by this expression here. So you can think about this expression as 1 over viscosity of this dashpot. Okay, A is a material parameter, N is another material parameter, Q is the von Mises stress, and D is the damage parameter that starts from 1 if the material has no damage at all. So I'm sorry, it starts from 0 if the material has no damage at all. The material is undamaged, and it slowly starts to increase to 1, and when it reaches 1, this value spikes. So for a constant stress, if damage approaches 1, the strain rate approaches infinity, which is what we want to model here. So if suppose the stress is constant, but this damage approaches 1, it starts to get closer to 1. It makes for a constant stress, it makes the strain rate to increase, which is what we see here. Okay. Before talking about damage, notice that we have used stress, the stress tensor here, and not the deviatoric stress. And the reason is because when we have damage, the presence of damage, what I mean by damage is the presence of small cracks inside the rock salt. And those small cracks, when they open, when they are created, they occupy space. So actually, they do change the volume of the sample. And that is why we use the stress and not the deviatoric stress. Okay, so now let's talk about the damage evolution equation. I'm presenting here one model that one possible model for damage evolution, which is given by this expression here. So here we have the damage rate, or the time derivative of damage, equals an equivalent stress divided by B. B is a material parameter. D is the damage to the power R. R is another material parameter. This equivalent stress is given by this expression here. This is the von Mises stress, Poisson's ratio. This is pressure, which is minus the mean stress. Q is the von Mises stress. And this is the equivalent stress that we use here. So we see if the stress is constant, the sigma star will be constant, will be positive. Suppose we're in the beginning of the simulation and damage is 0. So we have the damage rate will be a positive number here. So this will be sigma star over B to the power R. So damage rate, so this equation will be a positive value, which means that damage will start to increase over time. Okay, for a constant stress. Now, to compute the strain rate of this damage, we need to compute damage, and damage is given by this expression here. To calculate this damage value, we can solve this ordinary differential equation. It can be solved analytically if we know the stress. If the stress is constant, this has analytical solution. If the stress is well behaved, we cannot. I'm sure we can also come up with an analytical solution for that specific stress condition. But for a general stress, it's hard to solve this equation analytically. It's better to solve this equation in a numerical way, and we can do that using Newton-Raphson, and I'm going to show how to do this now. Okay, to solve this equation using Newton-Raphson, first we need to define a residual equation, which is given by this expression here. K is the iterative level. The time derivative of damage can be approximated by this expression here. So D at current time level iteration K minus D at the previous time level, which I know. I don't know the damage at the current time level, but I know the damage at the previous time, divided by the time step size, and then I have this term here. What I want to find out here is what is the damage that I have to introduce into this equation such that the residue is zero or at least below a certain value, specified value. Okay, so this is the residue. Now comes the Newton-Raphson. We say that the residue for the next iteration k+1 equals the residue of the previous iteration, rk, plus the derivative of residue with respect to damage multiplied by the variation of damage. So damage k+1 minus damage at iteration k. And this, according to the Newton-Raphson method, has to be zero. So this residue has to be zero. What I don't know in this equation is the damage at k+1. So I solve this equation for dk+1. I know the damage value at the previous iteration, k. I know the residue at the previous iteration, which is this expression here. The derivative of this expression with respect to d, in this case, we can calculate this derivative by hand analytically, or we can use finite difference. So in this way, we can update the value of damage, and then we come back to this first equation, and we iterate here until this residue is below a certain level. Once we define the damage for a certain time, we can then compute the strain rate at time t plus delta t, because we know the value of damage. When we know the strain rate for the damage element, we can compute the strain at time t plus delta t just as before, choosing one of the integration methods that we like, explicit, full implicit, or Crank-Nicolson, because now we know how to compute the strain rates at the current time level and previous time level. Okay, so this is how we solve this this model for this dashpot. Okay, we are all assuming that we know the stress in this case, and we want to compute the deformation, the corresponding deformation, because that's usually the case when we perform triaxial tests. When we perform a triaxial test in the lab, we apply a certain stress condition. So we know the stress condition, and we want to compute, we want to measure the deformation over time. So we apply the stress in a laboratory experiment. We apply the stresses and we measure the deformation. And in this case, the model is exactly the same thing. We apply the stress, we know the stresses, so the stress I know, and I want to calculate the strains. I want to calculate the deformation. In lab, we do not calculate the deformation. We measure the deformation. So let me show you the behavior of this of a constitutive model with this damage dashpot here. Okay, so this is a problem. This is one of the so this is a triaxial problem that I'm solving here. I'm simulating. These are the stress condition. The blue curve is the axial stress. The red one is the radial stress. And we see that they increase in the beginning, but then they stay constant. This has to do, these two graphs here, they have to do with the viscoplastic model, but don't worry about them right now. And here in this, let me show you so that you can see better. This is the result of the resulting strains. The blue one is the axial strain, and the red one is the radial strain. And here in this graph, we can see the damage, the value of the damage evolution. It starts from 0, and it goes, by the end of the simulation, it goes to 0.7. So when you can see that even if the stress is constant here, when the simulation progresses, the value of this damage parameter increases, and at a certain point, it makes the deformation, the axial deformation and radial deformation to spike. And this is how we can model tertiary creep. Okay? Okay, let's move on. The last element is the viscoplastic element. The viscoplastic strain rate. I'm calling it inelastic here, but I could have used viscoplastic here. The viscoplastic strain rate depends on the stress and also depends on alpha. Alpha is a hardening parameter that I'm going to explain now. The expression goes like this. It depends on mu1, which is the material parameter, F divided by F0. F0 is a reference number, which is usually equals to 1 megapascal. F is a yield function, which is given by this expression. I'm going to explain that. These brackets here represent a ramp function. So if this F is negative, those brackets will return 0. So if F is negative, this whole number here is 0. If F is positive, then it returns the value of F. Okay. And this is raised to the power n. Power n is a material parameter. And all this entire number here is a scalar. F is a scalar. When I take the partial derivative with respect to stress, I take the partial derivative of F with respect to every single component of the stress tensor, which makes this a second order stress tensor. Not stress, but it makes a second order tensor, which is good because the strain rate is also a second order tensor. So this gives the direction in which the viscoplastic deformation will occur, and this gives the intensity of viscoplastic deformation. Now, in this case, I'm using the value of F here. This is actually the potential, should be the potential function. But in this case, the potential function equals the yield function, which means I'm using an associative model. Okay, now let's talk about the yield function, because the yield function is actually the threshold that I was talking a bit earlier. This threshold here is not actually a number, but a function or a surface. So this yield function is calculated based on alpha and the stress. Once we have the stress, we can compute J2, I1. I1 is given by I1 bar is given by I1, which is the first stress invariant, plus sigma T. Sigma T is the tensile strength of salt. So salt can support a little bit of tensile strength, of tensile stress, but not much. If we apply too much tensile stress to a salt rock, it will break. So, and that value in which the salt break under tensile stresses is called the tensile strength, which is this value here. Let me show you what this is. Okay, when I show this graph here, you see this small region here. This small region, this value here is the tensile strength. So the positive values of I1 means that we are applying only compressive stresses to the sample. Once we reach this region, it means once we have negative I1 values, it means we are applying tensile stresses to the salt rock. And we can see that we can only apply a little bit of tensile stress until it it hits the failure boundary. So if we apply tensile stress to a salt rock, it's very easy to hit the short-term failure boundary. That is where we observe the failure under tensile stresses. So to be on the safe side, we should always have positive values of I1. We should never go to tensile stresses. Okay, so that sigma t that we see over there, it's this value here. Okay, let's come back. Yeah, so we have I bar, n is another material parameter, gamma, beta 1, beta, m are all material parameters, and this function also depends on the loads angle, which defines the stress condition, if it's tensile or compressive or whatever. So it depends on stress, and it also depends on this hardening parameter. This hardening parameter is given by this expression here. A1 is a material parameter, alpha 0 is the initial hardening parameter, eta is also a material parameter, and xi is the accumulated viscoplastic deformation, which is given by this expression here, the integral between the initial time to the current time and square root of double dot product between the viscoplastic strain rates. Okay, this function here measures the distance between the stress and the threshold. Okay, so if this function is negative, it means that the stress is below the threshold, so there's no deformation. So if I throw for a certain value of hardening parameter, if I consider a certain stress, this function will give a certain value, positive or negative. If this value is negative, it means the stress is under the threshold. So if the f is negative, this function here this value is negative, those brackets will return 0. So this will be a 0 number, which means that the strain rate is 0. So there is no viscoplastic deformation. That is why we see no deformation, no viscoplastic deformation here. If this value is positive, it means that we crossed the threshold. So, and the more we cross, the further we are from the threshold, the more positive this value will be, the larger this value will be. Which means that this value here will be larger, meaning that the strain rate will be larger. Okay? So the moment that we cross this threshold, we start to have viscoplastic deformation. When we have viscoplastic deformation, the accumulated viscoplastic deformation starts to increase because of this expression here. So this number xi starts to increase. When xi increases, the value of alpha decreases. And when alpha decreases, the threshold expands, it increases. So if we think this as a yield surface, forget about threshold now, and let's move to a more general idea of yield surface. So the yield surface will be at the threshold now. The threshold is not just a number, but a surface. And I'm going to show in a few seconds what that is. So that yield surface expands when this alpha decreases. Okay. Okay. So let's see an example of how it works. This is the same example as before, right? But now we are going to take a look at these graphs below here. Let's go to the beginning here. Okay, let me explain. The graph in the bottom here shows the that one that I showed before, I1, or the mean stress, and square root of J2, or von Mises stress. What I'm showing here is the stress point. This point here shows the stress point, corresponding to this stress condition. So I'm applying this radial stress and this axial stress, and if I compute I1 and the square root of J2, it gives me this point here. In the very beginning, the point is this one, and we can see how it moves when we increase the axial strain and radial strain. Okay. Now, this gray curve here represents the yield surface. The yield surface is given by this expression here. So if we make this expression equal to 0, when this yield function equals to 0, it defines the yield surface. So along this gray line, we have the yield surface. We can see that in the beginning here, the stress is under the yield surface, which means it's under the threshold, so there is no viscoplastic deformation. And we can see that by looking at this graph here on the right. I hope you can see my cursor here. So this graph shows two things. In red, it shows the yield function value. So you can see that 0 here. So by now, this value here is below 0. Okay. Meaning that the yield function is negative, which means this number here will return 0 because F is negative, so there is no viscoplastic deformation. Okay. And the blue curve here shows the hardening parameter, which is alpha. And we can see that when we start to increase the stress, let me go little by little. Yeah, you see, when I increase the stress, we see that we approach the yield surface. If we keep increasing the stress, let me give a zoom here. If you keep increasing the stress, the value of the yield function also increases. At a certain point, the yield function starts to be positive, which is exactly when we cross the yield surface. When the yield function is positive, we start to have viscoplastic deformation, and we can see the response to the material deformation here. So if we look, for example, at the total strain, the axial total strain, we can see that when the stress increases, the material behaves like this, but at a certain point, it sort of jumps. There is a jump in the deformation. And let's see when it happens. So you can see that now we have viscoplastic deformation, and the yield surface starts to expand. And the reason it expands is because the hardening parameter starts to decrease. You can see the hardening parameter, the blue one, the blue curve starts to decrease. And because the hardening parameter decreases, the yield surface expands. So it moves towards the stress. Yeah. So you can see this. You can see how it moves towards the stress. And now the stress is constant. The stress is constant, and the hardening parameter is still decreasing, but not as much as before. And also the yield function, it increased up to a certain value, and then it starts to decrease, but it's still positive. You can see here, this is the 0 value, and it's still positive. If it's still positive, it means viscoplastic deformation is still occurring. So you can see that the more the hardening parameter decreases, the closer the yield surface is from the stress point. Let me speed up a little bit. Then we decrease. Yeah, when we remove the axial stress here, you can see that the point moves into the elastic zone, so below the threshold, which means, and therefore the yield function drops to negative values, meaning that there is no viscoplastic deformation anymore. But then we have increased the yield surface. So we keep here, and then we come back. We can see that when we start to load the sample again we cross that yield surface, and we observe a new jump here. You see, let me come back a little bit. Yeah, you can see that when we start to increase, when we increase the stress again, the axial stress, after a certain point, we cross that yield surface, and that triggers additional deformation. You see the yield function becoming positive, and now the hardening parameter will drop again, which makes the yield surface to grow. And we see the jump here because now we have viscoplastic deformation. Okay. Yeah. So let's see the initial yield surface. Just a second. Yeah, so here it is. So this is the initial yield surface, or the initial threshold. By the end of the simulation, the yield surface is quite big. Yeah, you see. Now there is a very large region that we can move here without triggering viscoplastic deformation. Okay, so basically this is how the viscoplastic element works. It's not so trivial as it looks, but this is how it works. And to solve this equation is also a little bit tricky, but yeah, we can also use the Newton-Raphson method just as the damage element. So because notice this, to compute the viscoplastic strain rate, we need the hardening parameter to compute the yield function. Right, the yield function depends on the hardening parameter, but and to compute the hardening parameter, I have to use this equation, which depends on the accumulated viscoplastic strain. And the viscoplastic strain depends on the viscoplastic strain rate. But the viscoplastic strain rate is exactly what I want to compute in the first place. So to compute the viscoplastic strain rate, I need the hardening parameter, which requires the accumulated viscoplastic strain, which requires the viscoplastic strain rate. You see, so this is a nonlinear problem, and we can use Newton-Raphson to solve this problem. And the way we do it is by defining a residual equation like this. This is the hardening rule. We define the hardening rule. What we want to do here is to find what is the value of the hardening parameter that I introduce into this equation that produce a residual equal to 0. Notice that although you only see alpha here, but actually the accumulated strain rate, the accumulated viscoplastic strain also depends on the value of alpha. So alpha is also here. Okay, so to solve this problem, we use Newton-Raphson. So the residual at the next iteration k+1 equals this expression here. So I make this residual to be 0, and I solve for alpha at iteration k+1. Alpha is given by this expression, so I know alpha of the previous iteration. I know the residual, of the previous iteration, which is given by this expression. I know alpha k. I want to know alpha k plus 1. And to take the derivative of this expression with respect to alpha, I think it's very hard to do it by hand, if not impossible to do it by hand because of this term here, alpha. This term also depends on alpha, and it's very difficult. So I would recommend to compute this derivative using finite difference. So once I have alpha at k plus 1, I return here and I check the residue and I keep iterating here until the residue is below a certain level, a certain tolerance. Once I obtain the hardening parameter, then I can compute the viscoplastic strain rate at the current time level, T plus delta T, in this expression here. When I have the viscoplastic strain rate, I can compute the viscoplastic strain at T plus delta T by this expression here, just as before. Okay, so now we know the behavior of each individual element isolated. Now we want to combine, we want to discuss how to combine those models in order to produce the behavior that we want. But the good thing about this next part of presentation is that we don't need to show equations anymore. We just have to, we already have all the equations that we need. We just need to think about how to combine those elements. So let's not forget our goal, what we have to model. What we want to model is transient creep, which is this first part here, steady state creep, which is this part, and tertiary creep, which is this part. And in addition to that, we want to model reverse transient creep. These are the behaviors that we want to describe with our constitutive model. Okay, so let's first consider our first model, which is the Maxwell's model, which is called the Maxwell model, and this is a very known constitutive model, and this is composed of a spring in series with a dashpot. Now, when we apply stress to this dashpot, this same stress is perceived by the dashpot and also the spring. So this is important to have in mind because it means that the spring will respond to this stress independently if it's connected to a dashpot or not. The spring only responds to a stress. It doesn't care if it's connected to a dashpot or whatever else. If it perceives a certain stress, it will respond to that stress. The same thing for the dashpot. If it perceives a certain stress, it doesn't matter to which type of element it is connected to, it will respond to the stress it is perceived. And if we apply a stress here, the stress sigma, the dashpot will perceive that same stress, and the spring will perceive the same stress, and they respond independently to each other. If we remove this dashpot here and we apply the same stress, the spring will respond exactly the same way. The behavior of this spring doesn't change by the presence or not of this spring. It only changes according to the stress it perceives. Okay, and this is important because it makes really easy to understand what is the behavior when we of this model when we apply a stress condition, because we know that a springs isolated or in combination with other elements, it will respond like this. If we apply this stress, it will respond instantaneously. If the stress is constant, it will stay constant. When we remove the stress, it recovers completely. And for the dashpot, it deforms at a constant rate. And when we remove the stress, it stops the deformation and it doesn't recover. And the total deformation of this model is given by the summation of the individual deformations of each individual element. So it will be given by this blue curve here. So we can see that when we apply the stress, this model responds instantaneously, and then it deforms at a constant rate. When we remove the stress, it recovers a little bit because of the spring, and then it stays at a constant stress. Now, if we look at the target, what we want to model, I wouldn't say this is a very good model, but it's not completely bad at all, because we can model the instantaneous elastic deformation here, and we can also model the secondary creep with this type of model. And if that is enough for your application, we are good to go with this simple model. But it completely misses transient creep, tertiary creep, and reverse transient creep. And if those deformation mechanisms are important, then we should model them as well. And that is what we are going to try to do now. Now, from this Maxwell's model, we can replace this dashpot by a Kelvin-Voigt element like this. So we have a spring in parallel with a Kelvin-Voigt element, and this is called a standard linear model. It's a very well-known model for viscoelastic materials. It's called standard linear model. Okay, again, this Kelvin-Voigt element perceives this stress sigma, and it responds as if it's not connected to anywhere else. So the deformation of these two elements are independent from each other, such that the total deformation is given by the summation of the individual contributions of each element. So this will be given by this blue curve here. Now, if we use this model to represent a salt behavior, I wouldn't say it's a good model, because it completely misses almost everything except by transient creep and reverse creep. And even transient creep, it's not, I wouldn't say this element can completely describe transient creep, although it looks like. There are reasons that we can show that this element is not appropriate to describe transient creep, although it is appropriate to describe reverse transient creep. Okay. Now, okay, so the problem with this model is that it completely misses secondary creep, right? So what if we plug Dashpot in series with this model? If we do that, the model is called Berger's model, which is also a classical constitutive model. This is composed by a spring in series with a Kelvin-Voigt element, then a Dashpot. When you use this model, it seems like it's getting closer to what we want. You see, we have something that looks like transient creep here, and then it becomes constant because of so we are able to model secondary creep or steady state creep because of this Dashpot. But when we remove the load, we see that it recovers too much. It seems to recover too much because most of the deformation in the beginning here, most of the deformation in the beginning is because of spring and the Kelvin-Voigt. The Dashpot has almost no deformation in the beginning. So when we remove the load, the spring and the Kelvin-Voigt element will recover almost everything. It will recover completely. So when we remove the load, the spring and the Kelvin-Voigt element will completely recover, but the Dashpot will not recover. And if we look this graph here. Of course, this is just an illustration, but this is too much. In reality, when you look at experiments, we see that when we remove the load after transient creep, when we remove the load, it doesn't recover that much. It just recovers a little bit, meaning that most of this deformation is not actually recoverable. It's actually inelastic deformation. That is why I argued before that the viscoelastic element, the Kelvin-Voigt element, is not appropriate to describe transient creep, because transient creep is actually an inelastic deformation. Okay, that is the reason. So what if we replace this viscoelastic element by a viscoplastic element, like this? Then we will get something like this. In the beginning, it's almost the same. It doesn't change. But when we remove the load, we see that only the spring recovers. That is why we have this sharp deformation here. And it stays like this. The viscoplastic element doesn't recover at all. The dashpot doesn't recover at all. Only the springs returns to its initial configuration. It looks a little bit better in terms of recovery here, but still we are missing the reverse creep. So let's add the viscoelastic element, the Kelvin-Voigt element, back into this model. Now we have something like this. We have transient creep here, steady state creep, and most of the deformation during transient creep is captured by this viscoplastic element. And when we remove the load, although the viscoplastic element does not recover, just like the dashpot, the viscoelastic element will recover, and it will produce a transient creep, or what we can use to model transient creep, like this. And now we are closer to this situation here. So with this model, we are able to model transient creep, steady state creep, and reverse creep. So it's getting closer to what we want. Now, finally, we have to figure out how to model tertiary creep. And for that, we just add that special dashpot by the end of our model. And that dashpot, if we apply a constant stress like this, all the individual elements would behave like this. So this dashpot will deform at a constant rate. The viscoplastic element deforms in the beginning and then it stays constant. Same thing with the viscoelastic element, but the damage element, it will produce basically no deformation at all, and then it spikes towards the end of the simulation. Therefore, we could describe tertiary creep as well. So to summarize, our constitutive model to capture transient creep, to capture all the deformation mechanism that we described before, would look like this. So we have a spring to capture the instantaneous elastic deformation. We have a viscoplastic element to capture transient creep. We have a dashpot to capture steady state creep. And we can also have a different dashpots to capture dislocation creep and also pressure solution creep, and also dislocation glide. You can have many deformations during steady state creep. We have a special dashpot to capture accelerated creep. We have used this dashpot here, but we can also use, and this is very common in the literature, to use not a dashpot like this, but the concept of effective stress. So the damage enters in the computation of the stress. It's like a perceived stress. So the effective stress would be equal to the stress divided by 1 minus d. And as d increases, approaches 1, the effective stress increases exponentially. And that is another way to include tertiary creep instead of including an isolated dashpot as I done here. But to include the dashpot is easier to think, is easier to explain. I'm not so sure about the comparison of the two approaches, but anyway. So this is for accelerated creep. And then we have added a Kelvin-Voigt element with the specific purpose to describe reverse creep. So this would be the complete constitutive model for salt mechanics that can capture all these deformation mechanisms. Now, it's very, as a last comment, in the SafeInCave simulator, we did not implement the tertiary creep. So this is the model that is implemented in the SafeInCave simulator. And the reason is because we are not interested in predict how the tertiary creep will develop. We just want to predict if there is going to be tertiary creep or not. So if we apply a certain pressure condition inside the cavern, and we compute the stresses around the cavern, and we identify a point that lies on the dilatancy boundary, we know that we have to change the pressure conditions, the operation conditions of the salt cavern. Yeah, when we change the operation conditions and we check the stresses around the cavern, if all the stresses are in the compressibility region, then we know that that operation condition is good. That there won't be tertiary creep, and therefore there will not be any mechanical instabilities. We don't need to know how tertiary creep will develop. We just need to know whether it will occur or not. And to know whether it will occur or not, we don't need to. We just have to look at this graph. We don't need to actually model tertiary creep. Unless the presence of that dashpot completely changes the stress distribution. But that is something to investigate. But for now, the constitutive model implemented in SafeInCave is just this one. Okay, so to close this presentation, we have discussed here the mechanical behavior of salt rocks. I have shown the macroscopic overview of how a salt rock behaves under certain stress conditions. We have shown transient creep, steady state creep, tertiary creep, and reverse creep. And those are the main deformation mechanisms that we try to model in our constitutive model. And to do that, we have seen the mechanical behavior of simple basic elements such as springs and dashpots. We have shown the intuition about that mechanical behavior and also a detailed description of the equations that describe those behaviors. And once we have understood the behavior of those individual elements, we discussed how to combine those elements in order to produce all those four deformation mechanisms. So transient creep, steady state creep, tertiary creep, and reverse creep. Okay, so thanks for watching, and see you next time.